you have any questions? More questions? Okay, so let me go back to Simeon Philip pointed out that I wasn't clear enough about this business of distributions and currents. In fact, I wasn't very precise on one thing, is the following thing. So the distribution D, the distribution, so there is some confusion in some sense intrinsic in the way people use this. The distribution is a functional on functions, but we also think of this as a generalized function, right? In some sense, we also think of the distribution as a generalized function. But as a functional on functions, it's really a current. It behaves like a 2 form, so it's really a current of degree 2. So like a 2 form. So the way it goes is that we have we fix an area form. So since we have fixed an area form, so we have an identification between between currents of degree 0. They are identified with currents of degree 2. So in this sense, we can view a distribution as a linear function on functions, but also as a linear function on 2 forms, just by using this identification. This showed up in the formula that I wrote that d dot ix area, the action of this on a 1 form contains this d of ix area. Ix area is a 1 form wedge alpha, so this is alpha was a 1 form, but then I have to divide by area. So it depends on how I interpret d. So if I interpret d as a function on functions, I have to divide by area. If I interpret d as a function on 2 forms, I don't have to divide by area. So it's just a kind of a, there is this identification which basically you can sort of neglect to make explicit, and this may cause some confusion. So anyway, so this is, I guess, is this, or maybe I continue here for the moment. So let me recall that we have a theorem that basically says the following: says that for almost all x, or for the Anosov case, for pseudo-Anosov case, and we have a space, and for every s large enough, there is a space Ix S minus S, which is a space which is in this Sobolev space. This is a space of x invariant distributions. With the property that if f, for every f in the Sobolev space, and also in the kernel of this space of functionals, there exists u, which will, with some loss of derivative, solving the equation xu equal f. So that's basic result, and then that I mentioned last time. And then I also sketched the fact that given d in Ix, well, when I don't put an s, it means that I take all possible regularities, so I take all of them. There is a map. There is a map from d. There is a map made of 2 steps. The first step is the flux current. and the flux current is closed in the sense of its boundary is 0 or its zero derivative is 0, and so it has a cohomology class. Let's say that all this is real. A priori, this could be complex, but since the dynamics is real, the flow is real, we can always take real parts. And this map is not onto, but is onto. So the image of this map maybe I'll call it C from Ix to H1. Is exactly this set of cohomology classes that have pairing with the class, the dual class to the flow, equal to 0. So in particular, this has dimension 2g minus 1. It would be useful to consider the space of such flux current. So the space of flux currents. I denote, well, yeah, I can consider certain regularity. I denote it with B minus Sx M. So this is the space in W minus S. The B stands for basic. So these currents are called basic. That's not my invention. There is a terminology in theory foliation that a current is called basic. Basically, well, it's called basic if it does this. Well, the definition is a bit, but so C, a current. Oh, I'm using C for something different. Yeah, let me use maybe some different letter for this map. I think in my notes I use C for both, but yeah, maybe I'll use a rho for this. No, rho is Ruelle. Yeah, my choice of notation is not ideal. Let me call it class of C. Because in fact this is, so the C will be the current and class of C would be the map. So if C is a current is basic, it's called basic if two things happen. The contraction of the current with respect to x is 0, and also the the Lie derivative of the current is also 0. And well, since there is a formula that says that the Lie derivative is equal to the contraction of the exterior derivative plus the exterior derivative of the contraction, this implies that, well, not always, but for currents of degree 1, so C of degree 1, basic is also closed. So all basic currents are also closed. So you can check that if we use the fact that this is Lx of C is 0, then and Ix of C is 0, then we get that Ix of dc is 0. So from this we get that Ix of dc is 0. And if C is of degree 1, then dc is of degree 2, and the contraction cannot be 0 unless dc is equal to 0. So there is a close relation between being basic and being closed, provided the degree of the current is I'm not sure in general, but certainly it's true for degree 1 currents, and degree 1 currents are the ones that we are interested in. So I recall that degree 1 currents are like 1 forms and also like curves. So they act on 1 forms, and they are like 1 forms because 1 forms act on 1 forms by wedge and integration. So degree in dimension 2, degree and dimension are, well, when you have degree 1, you also have dimension 1, because degree and dimension are complementary. Put this up. And now what I'm going to state is a structure theorem for all these objects, because so far I just told you that this map is surjective, but this cohomology map is surjective, but I haven't told you much about the space is supposed to be infinite dimensional in general. So there are lots of distributions and lots of basic currents associated to them, but only, I mean, we have a map, a surjective map with finite dimensional space, but we have to say something about the rest. So there is a sort of a structure theorem. A question? Yeah.
Surjective under some conditions on X, like for the
Yes, yes. X is all. Yeah, this is a good question. What are the conditions on X? So X certainly can be taken generic, almost all, with respect to any SL2 invariant measure. In fact, it can be taken to be almost all directions on any surface, or it can be taken pseudo-Anosov case. Now, it's probably true more generally, because you can. The question is, how far can you go with the Marmi Moussa Yoccoz argument? So right now I'm not sure what measure can be covered, but yeah, roughly the almost all with respect to, say, all SL2 invariant measures. This is a safe statement, and also periodic orbits. This is also true, but there are certainly other cases where one can actually have a statement almost all X's with respect to some Teichmueller invariant measure. But I'm not sure that this has been kind of worked out. So as far as I know, no. Yeah. So the structure theorem for basic currents basically says the following: it says that there is a certain exact sequence. Well, that's one way to put it. So here we have R area, and then here we have the basic currents of order. Minus S plus 1. And here we have the basic current of order minus S. And here we have this, this space that I called H1X. I should have introduced the notation. And then we have 0. So this space is exactly the space of C's, such that IX area wedge C is 0. So this is there. So this map is onto, and this is the cohomology map. And so what I'm saying here basically is that if a basic current is has 0 cohomology, then it comes from another basic current. So the main point is the main statement here, besides the surjectivity that I already mentioned, is the fact that if the cohomology class of, so if C is basic, and the cohomology class of C is equal to 0, then there exists C prime, which is also basic, but of course we gain, we gain one derivative, such that, well, what is the map here? The map here is the derivative, the Lie derivative with respect to the y vector field. So you can say it's the y vector field, such that C is equal to Ly of C prime. And well, that's not hard to prove. So I can try to give a proof. So the proof is simply this. So C, a basic basic object will look like this with xd equal to 0. And now we know that there exists C prime such that dC prime is equal to C. And so first of all, C prime has to be of the form D prime wedge IX area. And the reason for that is that wait, what is the simplest way to do this? Yeah, I think this is true because because otherwise there would be a term that doesn't appear in C, which there would be the one form that is given by the contraction of the area with respect to y, and then it's also true that since IXC is equal to 0 because C is basic, then this is also shows that LX D prime has to be equal to 0. So D prime is also X invariant. So D prime is X invariant. So this is basically, so it's, if you write it in coordinates, it becomes pretty clear. So the fact that IX area is basically dx or dy, depending on your coordinates. And if you look at what this differential gives, C prime cannot contain the other differential. And then you have the fact that the contraction giving you 0, since this is a derivative, then you obtain that D prime is also X invariant. And then once you have that, this differential can only contain Y derivative. So you get basically that D is equal to Y D prime. Also from this. So that's a sketch of the calculation. So it's not especially enlightening. And you can think of this D being a function and IX area being dx, and it works fine. So then this is an important operator, by the way, that allows us to generate more basic currents, and so more invariant distributions. If we have given some, then we can continue producing more and more by this operator Ly. So then we have the following proposition.
What's the relationship between basic currents and flux currents?
The flux currents are special types of, is basically the same, you can say. So the flux currents are, so the terminology of flux currents is because they come from the definition of the flux currents for measures, which is a classical concept. But in the theory of foliation, they are usually called basic. But the notion of basic currents is much more general than the notion of flux current. So basic current is if you have any foliation, you can use this definition, right? You can say a current is called basic for a foliation if IXC equal to LXC equal to 0 for any x which is tangent to the foliation. Now, if the foliation is one dimensional, of course, you only have one direction essentially, so it reduces to this flux current for the flow. But flux current is kind of a very particular instance of that. So in this context, it's the same. So it's just a matter of terminology. So yeah, so this will give the following proposition that let's say something about the spectrum. So the proposition is that the spectrum of phi, so phi is a pseudo-Anosov map. Acting on Bx, so the space of all basic currents, is, well, it's going to be the following. It's going to be lambda, which is the dilation factor, and then it's going to be exactly coming from the spectrum of phi on the cohomology. So there is the mu I, and then there is lambda j, and here is I, well, I is going to be equal to 2g minus 1, and j is going to be equal to 0, 1, 2, etc. And one can add here that the spectrum, it follows here that the spectrum on invariant distributions is equal to, well, it's related, but you just have to divide by lambda. And the reason you have to divide by lambda is that the relation between basic currents and invariant distribution, where is the formula, is basically that a basic current is the invariant distribution multiplied times the contraction of the area by x, and we know that the area is fixed and the contraction by x is multiplied by lambda when you act with a pseudo-Anosov. X is just the expanding direction. So this means that when we pass from basic currents from basic current to distributions, we just have to divide by lambda. So here we get 1, and then mu I, lambda j, and now j is just start at 1. So that's the only difference. So that's what we get from this exact sequence, and from the fact that we have labeled the spectrum, the eigenvalues, the spectrum of phi on the cohomology, and then we go to distribution simply by this scaling factor that is caused by the presence of this form, which is a contraction of the area. Yeah.
Sorry. So in the exact sequence, it looks like so the map on the far left goes from like 2 forms to 1 form.
Yes, you're right. Good point. Should be this. Yes. Yeah. Yeah. This is the basic current that corresponds to the distribution constant 1, right? So it's the space of those currents that corresponds to just the invariant, the constant function. Okay. So yeah, it should be a 1 form. Yeah. Totally true. Okay, so at this point, remember that at this point we know more or less what we want to know about the action of pseudo-Anosov on these basic currents. But recall that in order to get Ruelle resonances, we have to deal with iterated coboundaries. So the question is, how can we study iterated coboundaries? And unfortunately, I guess I have to put this. Yeah, question.
But I'm trying to figure out what is the basic current. If I want to look just like two curves as currents, which one are basic?
Excuse me?
If I want to look at curves as currents, can I see which one are basic?
No curve will be basic for a unique ergodic flow. So in some sense, you would like to say that a basic current is it's an arc of orbit if there were no boundary, right?
So how
it should be closed, right? So,
huh? How are these related to foliating currents?
Well, in the theory of foliation, there is a notion of basic current that applies to general foliation. That's what I wanted to say. They are not really related to foliated currents. So you can take any foliation and ask Ixc equal to Lxc equal to 0 for any x tangent to the leaves, for any vector field tangent to the leaves, tangent to the foliation. That's the notion. If you look at the literature on foliations, there is this word, basic, and right, and then you can talk about the basic cohomology. For instance, you can construct a cohomology with these objects, and people in foliation theory do a lot of, prove a lot of results about about basic homology, for instance. In this case, it's very dynamical, and you of course you can prove results about basic homology, but that's exactly what we are doing, essentially, what I'm trying to describe. So, yeah, so at this point, I'm going to go into iterated coboundaries. And it's not very... I mean, unfortunately, there is the theorem about the cohomological equation is hidden, but basically, once you know how to solve the equation, it's just a remark that you can solve the iterated equation. So basically, iterated coboundaries. So the idea is that we would like to solve, say, we like to classify. So find all f's of the form, say x squared u equal f. Right? So that's the question. Then of course you can iterate. We can do find all f which are x cubed, x fourth, etc. But if you understand the first step, you understand all the nature of the question. So this is not hard because we know that f, if f belongs to the kernel of the invariant distribution, then, well, and is smooth. So let me drop. Of course, there are smoothness requirements that you can keep track of, loss of derivatives and everything. So if f is smooth, and it belongs to the kernel of the invariant distribution, then there exists a solution u with some loss of smoothness. So this is going to be less smooth, such that xu is equal to f, right? So now we like to solve, now at this point, we just like to solve the cohomological equation with given u. So simply we like to solve x u prime equal to u. And of course this can be done. If u prime belongs to the kernel, I'm sorry, not u prime, u belongs to the kernel of Ix. Right? So what does it mean that u prime belongs to the kernel of Ix, of these distributions, in terms of f? U. So we have to have, so if D is in Ix, we need, for every D in Ix, we need du equal to 0, right? And we can define D prime, we can try to define D prime of f to be D of u. Now notice that u depends on f by solving this equation. So if you want, you can say there is a green operator. Green operator is just a solution operator that says that u is some operator called green operator acting on f. This is the operator that gives you the solution. Well, so this distribution d prime is going to be just d applied to gx of f. Now there is a little, I'm cheating a little bit because of course the green operator is not defined on all f's. It's only defined on f's that satisfy the condition that f is in the kernel, right? So this linear functional is only defined on the kernel of Ix a priori. This is not a big deal because once you have a function on the kernel of on a subspace, on a closed subspace, you can extend it, say, by using Banach theorem, or maybe in Hilbert spaces you can just extend it to be 0 on the orthogonal. So d prime can be extended. To a distribution. Now this is Okay, so for every d, we have a d prime, and now we know that we need to solve all this condition d prime f equal to 0, because d prime f is equal to 0 is the same thing as du equal to 0, and so we can solve twice. Now, this is not very satisfactory. I'd like to point out that there is a maybe better way, which actually explains what d prime we are really looking at. So what is the equation satisfied by d prime? If you look at the definition of how to take derivatives of distributions, so the claim is that x d prime is d. This is basically by definition, because this means that d prime of x u is equal to d of u. Right? That's by definition. This it means, and this is for all u's. So this is just by definition, this equation means this, and we see that this is exactly, so if you call this f, this is exactly what we are saying here, that d prime is just the evaluation of d on the green operator, or if you want, you can look at here. Where is it? Well, I should call this u prime, maybe. No, xu should be f. That's correct. Xu should be f, and yeah. So d prime of xu is du. So this formula here. So this formula here, so if the distribution d prime satisfies that formula there, really satisfies this equation. It's just totally formal, just computing with these objects. So in other terms, we need to solve this equation, and then we need to solve it again and again and again. So then we need to define d2s, which are solutions of equations of the form x d2s equal to d primes, and so on. Okay? So in this way, we construct by integrating with respect to the flow, we construct a larger space of distributional objects. So we get a I x infinity is the space, which of course infinity means that I can do this operation an arbitrary number of times, or if you want, I can define Ixk is the space of k iterated solutions of equations x d prime equal to d, starting with d an invariant distribution. So you start with invariant distribution and then solve, iterate the solution of the equation, the Lie derivative equal to d. And you get a space Ixk. And of course, if you take all these spaces together, you get a space Ix infinity. This is the space of the relevant space of Ruelle eigenstates, basically, that can be constructed by starting with construction of invariant distributions, and then by this operation of integrating with respect to the flow. And this can be done based on the theorem of the cohomological equation. As I try to explain here, we can always integrate a distribution. So that's a, maybe I should make this clear in a remark that given the theorem solving the cohomological equation that I for functions the equation xu equal to d can always be solved for d vanishing on constant functions. There is this I mean, one would like to work with everything of zero average, no constant function, in the convex constant function. And the reason is that the reason is the following. The reason is that we can, what does it mean, the equation? So explanation, not even proof, explanation. So what does it mean xu equal to d? It means that u of xf is equal to df for all f, right? So now the point is that the set, the space of all xf's is for f smooth. This is a closed subspace. So we have defined u on a closed subspace, right? So provided this definition is well posed, and is well posed only if you look, the only issue is that maybe there is an f that belongs to the kernel of x. If there is an f that belongs to the kernel of x, then there will be a problem because d of f may be not 0 and u of 0 has to be 0. So the problem here is really the kernel of x. So I should have said here under the hypothesis that x is ergodic, or even minimal. So if the flow of x is minimal, then the kernel is given by constant functions, and so I only have to worry that d on constant function is 0 to make this a well-posed definition. So I just take this as a definition, take it as a definition of u on the space xf. Right?
When you mean closed subspace, you mean which functional space?
Yeah, good point. So I'm sparing everybody the fact that all this should be done in a Sobolev space. So this is the simplest way to do it. So really, when I say smooth, I should say finely smooth with S Sobolev derivative. But it doesn't really matter. I could use C infinity or the version of C infinity that I have on the surfaces, provided that this is going to be a closed subspace in that space. This is a Frechet space, but still a closed subspace. And then I only need to say that if I have a continuous function defined on a closed subspace, I can extend it to the whole space. And that's the solution. So this can be done in Banach spaces, Hilbert spaces, using Sobolev spaces. So this equation can be the thing that really matters is that the range of x is closed in a relevant space, and then we can just define our solution there and then extend it in any way. Of course, the solution is not unique because we know that x as a operator on distributions has a kernel. So there will be many solutions, but we take all of them. So we just keep going with this procedure and take all of them. So in this way, we construct all Ruelle eigenstates, and well, I mean, I haven't proved that they are so, but that's the case. And yeah, so it was here. And so what happens to the spectrum? Now, remember that earlier we were taking derivative with respect to y. And so taking derivative with respect to y produces this division by lambda, because y is scaled by lambda minus 1. Now we're integrating with respect to x, so the effect is going to be the same, because x is expanded, but now we are integrating. So the effect of taking derivatives with respect to y and producing all these invariant distributions and all these basic currents that had the effect of dividing by lambda, well, when we integrate with respect to x, is also as effect of dividing by lambda. So basically, we can say that a proposition, the spectrum of phi acting on I x infinity is is the same. Is 1, and then mu I lambda j, where I is 2g minus 1, and j is 1, 2, etc. So, but of course we obtain the same exponents at the same level. Exponent of this form at the same level can be obtained in different ways, because we can integrate and then integrate on one side and take derivative on the other side. And okay. So
the multiplicity is given by this.
yeah, the multiplicity, yes. Yeah, I was just thinking about that, so maybe I raised the remark. So the multiplicity is given exactly by the fact that if we pair these two operations, provided we don't have constraint on the, we don't worry about the regularity. So we start with D that as eigenvalue, say for instance, mu I divided by lambda j. Then we can consider all x, k, y, k of D. And I guess that this is like, of course, for k equal to, we have all this D, and then, and this will give us a basis. And now the point is that for k, so at some point, basically at some point, we have that xk d is equal to 0, and so also xk yk d is going to be equal to 0 because of commutation, and this happens exactly at k equal to. So it depends on j. So what is the right answer? So if j is equal to 1, we are looking at an invariant distribution. So I guess it happens exactly at j. Yeah, k equal to j. So this means that we can go with this. We can go only up to j minus 1, right? D dot dot dot, and then j minus 1, and at k equal to j, this is xj d is 0. This is determined by the j here, and so we got xj yj equal to 0 as well. And so this is the way of producing multiplicity, and in fact, counting multiplicity, because these two derivatives with respect to the eigenvalue work in opposite ways, right? Y divides by lambda, and the x derivative multiplies by lambda. So the total effect is neutral, and we have the same eigenvalue. Okay, so All right, so any questions? So I think at this point, maybe instead of going into how really you prove this, basically the proof of this is more or less the same as in the toral case, except for the fact that we have to take into account that we have all these eigenvalues. But I shown at the beginning that in the toral case how to handle the remainder term. The remainder term is basically handled by the fact that the remainder will be given by a function on iterated coboundaries, and the LM at the beginning said that if we look at correlation of k iterated coboundaries, they decay at some speed depending on k. So the larger k, the faster the speed. And in a torus case, that was all the story. There were no other eigenvalues except for one. And the argument will be the same here. It's not especially enlightening, so it's just basically a calculation. The main point is that we know enough about the spectrum and about how to handle the remainder term to make it work. So I should stress that we don't know much about a larger space of distributions. We only know exactly, essentially, the so-called Ruelle eigenstates. These are this Ix infinity, plus some information, some information on the fact that by the fact that we can solve this iterated cohomological equation, the remainder term is going to be negligible. So,
I have a question about that.
Yes.
So when you have a pseudo-Anosov, if it's for a quadratic differential and not for a holomorphic one form, then usually the eigenvalue of cohomology is not the same as the eigenvalue for actual.
Yeah, no, this is is not for quadratic differentials. Yeah.
So it's not any pseudo-Anosov.
Yeah. Sorry. Yes, orientable. Yeah. With orientable. Yeah, I mean, if the foliation cell is orientable, you can pass through the orienting double cover and then see what you can do there. And I guess probably there are statements that you can get by the same idea, but you don't want to do this directly on. Yeah. Yeah. First of all, there is no flow, right? And well, then the cohomological equation. I mean, it can be formulated in some way, but okay. So I would like to finish. Well, it doesn't matter. I would like to finish with some comments about what happens if we from pseudo-Anosov we go to Teichmueller flow. So we go from a periodic orbit to a generic situation. So since I don't have a lot of time, I will be a bit a cartoon of this. So basically, the way I want to think about this is the following. So we have a space of pairs. Now we don't consider just a pair of flow of vector fields, which is invariant under, well, contracted and expanded, but invariant under one map. We consider the space of all pairs. Now the space of all pairs should be considered up to isotopies. This will be the Teichmueller space, but let me consider the space of all pairs, and let me say that the moduli space is just a quotient by the action of orientation preserving B fields. And just do so this is basically the same as roughly like, well, you have to discuss strata and everything, but it's essentially the same as the moduli space of translation surfaces, at least caricature. And well, we can define cocycles. So we can define cocycles over the GT. GT is a Teichmueller flow. Let me recall, just to fix ideas, that GT, well, in fact, there is also an SL2R action, but let me focus on Teichmueller flow. Teichmueller flow acts just by taking xy extending it to e to the tx, e to the minus ty. And of course, this should be seen up to, I mean, the class, the conjugacy class under the action of diffuse. So if you think in this way, it's quite clear that if you have a periodic orbit, it means that for some value of t, these two classes are the same, and so there is an element of the group of diffuse that sends xy into some e to the tx, e to the minus ty. So this, at this point, should be obvious to everybody, I guess. And you will forgive me all the imprecisions in this definition, but I want to get to defining the cocycles. So the usual considerable cocycle basically works like this. We take the space of xy, and then we take the product. So this is a space, again, it's a caricature, but these are fixed surfaces, so certainly they are marked. And so you take the, say, the product with a cohomology, and then you do a quotient respect to the action of diffil, where diff acts on both factors. So diff acts on cohomology classes, it also acts on translation structures. And of course, so this is the space of the cocycle. What is the cocycle? The cocycle is just GT cross identity on above. So on the space, this is the space of translation structure cross the cohomology. So this again is a cartoonish way to say that I have a way of trivializing the bundle, and then I just use parallel transport to define the cocycle, and basically you can represent this kind of operation in this way. Now, the point is that we can replace this fiber by spaces of distributions. So we can define distributional cocycles, or maybe you want to call it transfer cocycles, where H1MR, where the cohomology, say, is replaced by some space of on the surface. And this space of distribution should not just be any space. I mean, it should be a space, but it should also be an Hilbert space or a Banach space. And the Hilbert or Banach structure should depend on the base point. So for instance, I could put there as a fiber the Sobolev space W minus S xy, or I could put the cycle of Ruelle eigenstates. Do that, for instance. There is a space for almost all x. There is a space Ix infinity at xy, and I can define what I may call the Ruelle cocycle or whatever, which is just this construction, but now the action of the cocycle is on the space of distributions. Now this is exactly the analogous of what we did for the pseudo-Anosov case. In the pseudo-Anosov case, we had a periodic orbit, so we had an action of the pseudo-Anosov on the surface, and we had actually eigenvalue for the action of the pseudo-Anosov on this space. Now we have a cocycle over Teichmueller flow, so this is a cocycle over Teichmueller flow by definition here. The definition is still this, so it's parallel transport, and we can solve the Lyapunov exponent. And in indeed, in this case, we can derive the Lyapunov exponents of this cocycle, which is an infinite dimensional. Well, you can say you can make it finite dimensional by taking Sobolev spaces of finite regularity, but if you take all of it as an infinite dimensional space with, say, Frechet fiber, one can describe all the Lyapunov exponents starting from this Kontsevich-Zorich exponent in exactly the same way I did for the pseudo-Anosov case. So the Lyapunov exponents are of the form, well, lambda 1 and then lambda I plus or minus lambda I divided by lambda 1 to the j, where, well, I is 2 g minus 1, and j is larger than 1. And what are the lambdas? Well, lambda 1, lambda 2, lambda g are the key exponent. So this can be done, and what is the point of doing this?
Are those the lambdas to the Ruelle cocycle, are they additive or
Oh, you're right. This is stupid. This is. Thank you for the remark. I think that's the correct formula, because I have to take these are like logs, right? So yeah, that's a good point. Yeah. So it's the same formula as before, but before I was dealing with eigenvalues, and these are exponents. So if I write the same formula, it's wrong, and I have to take the log of it, and that's what I get. And of course, lambda 1 is 1, right? So in fact, this means lambda plus or minus lambda I minus j. Lambda 1 is always 1 in the Kontsevich-Zorich cocycle, so that's what we get. Okay, so what is the point of this? Well, the point is that, of course, this describes the evolution under Teichmueller flow of certain distributions which are given by correlations on surfaces. Now, there is no system for which these correlations are correlations, so this may seem not very natural, and certainly is not very natural. So the only, and I guess I'll finish, I want to point out the only, this aspect of this that I think may have some interest. So the bottom line really is that we could do many things using the cohomological equation, but it's kind of a very ad hoc approach, because the cohomological equation we can solve only in very limited cases, and this business of cocycles over Teichmueller flow and deviation over ergodic averages is also kind of a little bit ad hoc for this case, but I think that it would be interesting, for instance, to replace this fiber, so replace H1MR by the Faure Gouezel Lanneau spaces. So the work of Faure Gouezel Lanneau is based on a definition of certain distributional spaces which are well adapted to the hyperbolic action of the pseudo-Anosov. And the main point is that the action of pseudo-Anosov is a quasi-compact operator. So, this is an important point. So I think that the same spaces will say that if we construct this transfer cocycle with the spaces, then we get a cocycle of quasi-compact operators, and then we can apply oscillator theorem. So then apply oscillator theorem. in infinite dimension. And this would give sort of a analytical proof of, say, the speed of conversion of ergodic theory that doesn't depend on the specific feature of the surfaces and may be suitable for generalization. So I think that the analytical tools are interesting, especially for generalizations, and it could be interesting to look at bundled version and isolated versions of this theory. Although it starts with the pseudo-Anosov case, I think it's something to say also about the generic situation. So in particular, one could, I mean, the issue is that once you have an isolated theorem, you have some, you could even imagine to prove results of the cohomological equation by purely analytical methods in the generic case, which now seems far, but it seems conceivable. So this is just a final comment, and I think I'll stop here.